Alrighty, guys, so thus far, what we have talked about with chemical reactions is collision theory, right? So things got to smash together, we got to break up the bonds in order to form new bonds, and things have to be lined up, right? They need to hit with the proper energy and with enough energy and proper spatial orientation. So they have to have enough energy to break the bonds. They have to have the proper orientation so that they're like lined up properly, so they actually like can snap to get back together to make the products. Oh yeah, then we looked at potential energy diagrams, so we could kind of follow the energy and see what's happening as the kinetic energy is turned into potential energy as the products make the activated complex and then fall back down. Or wait, let me take that and switch it around. When the reactants smash and make the activated complex and then form the product. But really, the product can also smash together, make the activated complex, and then make the reactants again. Remember, because reactions can go both ways, yeah? And we also threw in a catalyst. And all the catalyst does is it drops the energy of the activated complex so that the forward and reverse reaction can happen faster. It just lowers the activation energies of both the forward and the reverse, right? So the next thing I want us to look at are the whys. Like why? Why is it that like when the reactants smash together and break apart, why would they ever snap back together into something different anyway? Like why would they make something new? Why don't they just stay the way they are? Like what is forcing them? What is causing this change to happen? Like what are the underlying forces that are driving this? And it turns out there are two main driving forces in the universe, and we are going to look at both of them today. These are forces that cause everything, right? And it's maybe not a force like a push or a pull. It's these principles, these like sort of half hidden. It's like sort of hidden, like right in front of our face. These hidden driving forces in nature that cause every phenomenon that you will ever see to happen are governed by these two things. So let's dig into the secrets of the universe today, shall we? So the first thing I want us to look at, like what makes a reaction happen, like the reasons why, is this guy, enthalpy. And if you look really close, you actually might not need to look real close. I put that H in bold, right? So the reason I did that is because enthalpy is also called heat energy, right? Remember that enthalpy, delta H, right? The difference between reactants and products. Well, enthalpy is also defined as the heat energy of a system, or like how much energy is contained in a sample. And we're gonna use this word system here, because that way we can define what the system is, like what the sample is that we're looking at. So a little bit before we talked about like respiration, cellular respiration and photosynthesis. And so as far as the system goes, we can look at just photosynthesis and call that the system, right? And with photosynthesis, if we say just what's happening in the leaf, that is a one-way reaction. But if we define the system as the entire ecosystem that involves both photosynthesis and cellular respiration, then those things are reversible reactions. So the word system is kind of important because it is like what we are looking at, because perspective can change a lot of things. So this enthalpy, or this heat energy, you cannot directly measure it, right? Like you can't pick up a piece of paper and be like, oh, there's exactly 17 kilojoules of energy in here. There is no energiometer, none. The only thing we can do is measure changes, right? We can watch energy move from one place to another, and that's how we can know how much energy there was like a minute ago in our sample that we just burned. But we can't hold on to it and be like, oh, I know for sure. We can make really, really, really good predictions about how much energy is in there. For example, we can take 1 gram or like half a gram of a Snickers candy bar, and we can like put it in a calorimeter and we burn it and we get a certain amount of energy out. We do another gram, we burn it and we get some energy out. Now each time it's going to be just a little bit different, because each sample is going to be just a little bit different, and so we just use the average and say, okay, so for every gram we'll get like so many like kilojoules of energy out at a time. All right, so it's like, oh, in lab, I don't know if you guys, maybe not everybody's been around for lab, but like we took a candle and we burned it, right? Or you can like do this with potato chips and stuff. You burn a potato chip, and then you can like you burn it underneath some water, and you can use Q equals mc delta T, and you see how much energy went into the water. You guys get what I'm saying? Like, but there's no thing that we can like meter that we can hook up to a potato chip and be like, oh yeah, there's guaranteed this much. What we can do is we can make really good predictions, because you burn like 50 million 1-gram samples of potato chips, you're going to get a pretty solid idea of how much energy there is. But we cannot directly measure it. We just can't. And so if we head over to table I, on our reference table, what we've done is we've done chemical reactions over and over and over and over and over like 100 million times, and then we seem to get the same results each time, and then we say, okay, let's just put it in a table so we can just kind of look it up. So that's how we get calories from food and whatnot. You take 1 gram of potato chips, you burn it like not once, not twice, not 10, not 1,000, but like maybe 10, 20, 30, 50,000 times, like a lot of times, like many, many, many. You do it in this lab, you do it in that lab, you do it in the lab over in, I don't know, over in Spain, maybe one in Portugal too, and maybe over in Brazil, and everybody gets the same results, and we average them all together and say, okay, potato chips have this much calories in them. You get what I'm saying? So we can make good predictions, but there's no way to directly measure it. You gotta like make the energy move. Got it? I certainly hope so. So as far as enthalpy goes, or like as far as heat energy is concerned, right? Like heat energy, nature will almost always move towards states of lower enthalpy, of lower energy, right? That's what happens on their own. Things just always tend to go to lower energy, like rocks tend to roll downhill. You know, this is kind of the way nature is. So we also expect things to go in this exothermic direction, or in other words, losing energy, right? Because exothermic, if you remember, goes like that. So the overall energy drops, right? We expect it to go like into a lower energy because, one, it's moving towards a lower enthalpy or heat energy. It's losing energy, so it's becoming more stable. It's getting rid of like energy, and it lands down in a slightly more stable, less energetic state. The other thing why we expect things to be exothermic and also like lose energy is if you look at this activation energy over here for the forward reaction and compare that to the activation energy for the reverse reaction, the activation energy for the forward reaction is much smaller, and therefore it's just easier to happen because it just takes a slight nudge and boom, it goes. But the reverse reaction requires like a lot more energy, so it's just harder to make happen. So there are a couple reasons why enthalpy tends to like happen, right? And that's pretty much it. Now this next one, entropy. Now for entropy, we've got the R, and in this case, the R stands for randomness, because entropy is the disorder, the disorder or the randomness of the particles that make up a system. Okay, so we have subscript or the coefficient S, like just to like stand for entropy. So the greater the entropy, the greater the disorder. So that means like if something is neat and orderly, it has very low entropy. But if you like pick it up and shake it all around and make it totally messy, that's more entropy. And nature always moves towards greater disorder or more randomness. I mean, just look around at your world, man. Like I can clean up my desk, and in like 2 minutes it's gonna look like a bomb went off over here. There's no fighting it. It's like the law of nature, man. It's entropy taking over. So it just happens. Things become messy and less organized and less ordered just spontaneously, because that's the way nature prefers things to go. Like every single thing tends to go that way. Oh, it's kind of like these particles, right? See the little blue, I don't know, what is that, like a Fruit Loop? The blue and the red start out separate. So this is low entropy. That's like pretty ordered. There's not too much order. But over here, this is high entropy. This is like that. That's kind of what I mean by going ordered to like mixed up. It's like quite literally ordered and mixed up. And so this is one of the other driving forces of the universe. And this one is actually like really wild. This is the one that like sort of rules the entire universe. We're actually just discovering that entropy might be the cause of gravity. It's a little beyond. It's like just on the other side of my being able to really understand what they're talking about. Sure enough, they're saying that like entropy is what causes gravity. But look, what it really comes down to is like there's usually only one way for things to be organized and neat and clean. Like everything has a place and everything, you know, blah blah blah, whatever. So there's like one place where it's supposed to be organized. However, there are like a million other options for disorder. Now, if we look at like molecules and particles and stuff, it's sort of like if you had a big glass jar of Kool-Aid, right? And we add the Kool-Aid mix to the water, and we're stirring it, stirring it, stirring it. Now, most likely, once you stir it, it's going to stay all stirred and like all over the place, and it's going to be red Kool-Aid, because why would you have any other kind of Kool-Aid? I don't know. So if we have a big jar of red Kool-Aid, it's a clear glass jar, and we stir it, most likely, right? I mean, just statistically speaking, all those particles are gonna remain random. Now, it is possible. There is a statistical probability that all the red food coloring dye, I don't know, synthetic, whatever it is that makes it red, could collide all over the place in such a way that they coalesce in the center in the shape of a swirling unicorn, right? So all the red food coloring could smoosh together into like a 1-inch cube unicorn just spinning in the middle of our Kool-Aid. It's possible. It could. But what are the chances? What are the chances of that happening? I mean, there's at least a mole of molecules, which is like a very big amount of molecules. What are the chances of those all hitting all the water molecules and each other in just the right way so they could make a little teeny red unicorn floating in the middle of the Kool-Aid? Probably not. There's like, no, it's just like the chances of that happening are so slim. It's probably not gonna happen like ever. But how many other arrangements are there for the red particles to be, the red food dye particles to be just like everywhere? Well, like near infinite, man. Like there's a near infinite possibility. So you have like one option or like near infinite number of possibilities. If you have one option and near infinite possibilities, you're probably gonna be like landing over in the near infinite, right? So that's like kind of what entropy is and like why it happens that so much, because there's way more options for it to be like that. So that's kind of why things tend to go into like more entropy. And it happens so often that there is actually a law of nature. Notice it's not a hypothesis of nature, it's a law of nature, right? And it's the law of disorder, and it states that spontaneous processes, in other words, things that happen on their own, natural things that we don't mess with, always proceed in such a way that the entropy of the universe increases. Okay, so no matter what we do, entropy is going to be increasing. Also, fun fact, even if we do something to organize, like if I organize my desk, but we measured the system of just my desk, it would look like the entropy would decrease because it would become more organized. However, if we took a step back and looked at the greater system of both me, my environment, the metabolism it takes for me to move and think and organize and like everything like that, the entropy would still decrease. There is no process in the universe that can happen without increasing entropy. Full stop. If you can find it, one of two things, you're either doing something wrong or you just like broke science. So, you know. So let's check this out. Which has more entropy, an element or a compound? Well, let's check it out. If we were to draw a particle diagram of an element, it would look like this, right? All the atoms would be exactly the same and they would just sit there. Or what if it was a compound? Now, a compound, the compound is going to look probably more like this. Here, maybe I'll go like this. I'll do like a bunch of compounds there. So this compound is 1 red, 2 blue. Which one looks more mixed up? One where it's all red and uniform? Or one where it's all like mixed up and crazy, like where there's more. Yeah, this one, more entropy over there, right? It's more mixed up. So that's like, in like a chemical, in like a chemical formula perspective, right? Element, compound, chemical change. Now these next two, these are all about phase changes. These next two. So a solid, just like we had over there, is going to look like this, right? There's our container. There's the solid, it just sits there. Now a liquid, and also they're fixed in place, they don't go anywhere. Now the liquid is going to be kind of like much less organized. They're going to cover the whole area, and not only that, but they're going to be moving in every kind of crazy possible direction. They're going to be all over the place, right? So a liquid is going to have more entropy than a solid, because the solid particles are fixed, the liquid particles can like move around and go from one place to the other, and they can like mix themselves up pretty well. Same thing with a liquid or a gas, right? So the liquid, all right, let's make our little box. The liquid, it's going to be on the bottom. They can still move around pretty well, but compare that to a gas. Man, the gas is literally going to go all over the place and can mix up the entire container. So between a liquid and a gas is going to be more mixed up and random and crazy. So when you're looking at like entropy, right, remember the R is for randomness. So which has more randomness? Which is more mixed up? Element or compound? Obviously a compound, because it's got more things in it, right? The element has just one, compound has at least two. So there's more mixed up. Solid or a liquid? Well, definitely going to be a liquid, because liquids, they can move all over the place, and solids, they're stuck fast. Liquid or a gas? Well, it's definitely going to be a gas, because a liquid like stays in its little cup or container or whatever, but a gas goes anywhere, like fills the entire room, mixes up all over the place. You dig? So again, this here, the top one has to do with a chemical change, and the bottom two have to do with phase change. And it's always a good idea to separate these things out and keep them separate, because they are very, very different kinds of changes. All right? And that I want you to lock on for just a little bit later, what we're going to talk about here, which are spontaneous processes. These are things that happen all by themselves, right? Like melting, evaporating, all that kind of stuff. Things that just happen by themselves. So in a spontaneous process is a physical or chemical change that occurs with no outside help, like lighting a piece of firewood on fire. It just once it's burning, it is burning. However, spontaneous processes sometimes need a little added energy to get started. And we all know what that is, right? Some energy to get to start the reaction. Activation energy, right? So spontaneous processes sometimes need a bump, but they just go all on their own. We don't have to do anything to force it to happen. You just start it, right? So there are a lot of things that don't just go. It doesn't just happen. We have to work to keep it going, but that doesn't count as spontaneous. So what makes spontaneous things happen? Well, I'm going to tell you. Because our two forces, entropy and enthalpy, they work together to determine if a process is going to be spontaneous. However, entropy will always win out. Always. There is no time where entropy doesn't win. Now look, let's check this out. Rusting metal. Right? This is going from iron and oxygen. You see how it's like two different elements? And over here, let's go Fe2O3. It's going to make rust. Right? Actually, I think that might be FeO. I don't know. It's rust. They're combined. You guys get what I'm saying? So that is more entropy. That's why rusting just happens all by itself, because you're increasing the entropy. Also, moving to the right, if you look at diffusion, if we start here, right, we've got like water and we've got like food coloring in the middle, and it naturally just diffuses. So in biology, you guys learned about diffusion ad nauseum. The driving force was entropy. Entropy was causing it to diffuse because there are more options for being mixed up than being separate and like organized. Which is why nature prefers things to go and like diffuse. And then the third thing, this one's a little bit weird, so we're going to lock our brain onto it, is this one, the melting of ice. So that makes total sense because it's going from a solid where they're fixed in place to a liquid where they're moving all over. But however, if you look at this through the lens of enthalpy, right? So for this one, it's a little bit weird. Enthalpy, or heat energy, is actually increasing. And typically nature doesn't like that. Nature prefers enthalpy to decrease. However, the reason why melting can just happen all by itself is because the entropy is actually increasing, and this always wins. All right, the entropy always wins. So enthalpy, like heat energy, always wants to get lower, always wants low energy, way low energy. Nature's lazy. Nature wants the lowest energy possible. But more than that, nature is a slob and just doesn't wants things as messy and mixed up as possible. So that's why entropy takes over. So even though the enthalpy is increasing, something like a melting block of ice or even like an evaporating puddle is always going to happen spontaneously because the entropy is increasing. And that's why that happens like all by itself. Got it? Awesome. We are done for today. To review these things through our head, we're going to do a fine mess, and that's about all that I've got. And I hope that you guys have a super duper awesome day. I totally am, and I will see y'all pretty soon.